Okay, so we are just waiting on Dr. Glen Cooper to join us. And we will get started with talking about some cool content from our exhibit 1001 and all the information Dr. Glen knows about this specific time period. My name is Janine Sherrard, and I'm the Distance Learning Coordinator at the Michigan Science Center. Turn off my radio, I'm sorry about that. Doc. And I'm just going to turn my video off until he arrives. Oh, he's here. So I'm going to promote him to a panelist now, and here we go. And hello, Dr. Cooper. Can you hear us?
Can you hear me?
I can hear you now. Can you hear us okay?
Yes, sorry about that.
Oh, no problem at all. So we are currently recording, and I'm going to post you on Facebook Live now. We're not live yet, so that people watching on Facebook could also join us.
Okay.
And then once I do that, I think you should see that it is joining to Facebook.
Uh-huh.
And then people on Facebook will have questions and answers for you.
Okay, does that mean I should have my Facebook up and running?
You don't have to, no. You're probably going to start seeing it now. It's saying live on Facebook.
Yes, I see it.
All right. So, yeah, we are currently live now. So hello, everyone, and welcome to our Michigan Science Center virtual visit with Dr. Glen Cooper. I'm going to allow him to introduce himself and talk about his background. Dr. Glen.
Thank you. I'm a professor of history, and my main interest is in the history of Islamic science. I am a classicist also, and so Greek and Arabic are my main languages, and I like to study the transmission of Greek thought, philosophy, and science into the Arabic Islamic world, and just to see how things were changed and developed, and how the history of science really took off under Islam. So today, what I want to talk about is the role of physical models and instruments in Islamic science. Now I'm going to, I want to share my screen, but I don't see how to do that.
Do you not have that option? I think I could give you that option.
I had it, but I don't see it. Oh, there it is. I see it. Okay.
Yep, you should have it. There you go.
Okay.
And we can see your screen.
Okay, so I'm intrigued by the use of devices, both physical models and conceptual models, as instruments of thought and scientific investigation in Islamic science. And so I'd like to talk about three different episodes, three different devices. I want to talk about Ibn al-Haytham's camera obscura. I want to talk about Kamal ad-Din al-Farisi's investigation of the rainbow. And I also want to talk about physical models in astronomy. So I'll begin with Ibn al-Haytham. He was born in Basra in the middle of the 10th century, and he worked for most of his career under the Fatimid rulers. By most estimations, he was probably the greatest scientist of the world of Islam and one of the greatest scientists of all time. The quest to understand how vision works goes back at least to the ancient Greeks. Aristotle speculated about how it worked, and both Euclid and Ptolemy had sophisticated theories of visual perspective. But the most popular theory was called extramission theory. This was the idea that a visual ray was emitted from the eyes, had contact with the object of vision, and then returned to the eye, bringing the visual information back to the eye. The Arab philosopher Al-Kindi, who worked in Baghdad in the 9th century, was the first Muslim physicist of optics. He used empirical observations to disprove all of the ancient theories of vision except for extramission theory. And in his optical research, he also developed a new analytical technique called punctiform analysis, whereby each point of the visible object is perceived by a single individual ray. Now, even though Al-Kindi's theory of the visual ray was incorrect, he provided important groundwork on which Ibn al-Haytham did his research. And Ibn al-Haytham ultimately disproved the extramission theory, showing through a series of ingenious arguments that light from objects enters the eye only in one direction, that it is reversed in direction before it reaches the retina, where the image is then received by the perceptive faculty of the mind. What I mean is the image is perceived upside down. So Ibn al-Haytham pioneered both thought experiments and actual scientific experiments to understand the process of vision. So the first thought experiment consisted of this. He considered an eye directed at very distant objects, such as planets in the heavens. According to the extramission theory, the visual ray has two legs of its journey. The first leg is from the eye to the object, and the second is the return from the object to the eye, which carries the information about the object back to the person. Ibn al-Haytham reasoned that if the eye emitted a physical substance, namely the visual ray, it would be depleted before there was time for the ray to make its long journey and return, and that so many rays must be emitted to take in such a large section of the heavens that the eye would shrink in size. Clearly that does not happen, so some part of the theory must be wrong. He proposed that the supposed first leg of the light ray's journey is fictitious, that the only part that matters in vision is the light rays that come from objects to the eye. Now, Ibn al-Haytham was using a version of the scientific principle of parsimony, later known as Occam's razor, after the medieval English philosopher William of Ockham, who died in 1347. That principle is that when choosing between two theories that explain natural phenomena equally well, choose the one that uses fewer variables or has the fewest moving parts. Now, if you were not convinced by that thought experiment, Ibn al-Haytham built a simple device depicted in this slide to show how light enters the eye and produces a reversed image on the retina. A camera obscura, or what we call a pinhole camera, he used as a model of the eye. Now you can see, nothing doubting, that light travels into the box in only one direction to produce an image on the sensitive back part of the eye. No need for an emitted visual ray. Ibn al-Haytham's discovery set the science of optics on a course that led to the modern version of this science and was the basis of all subsequent discoveries in this field. I cannot stress enough the significance of these developments in the science of vision. Since observation with the eyes is the cornerstone of modern empirical science, it is difficult to imagine how scientific discovery would have proceeded as directly as it did to produce the modern world with an incorrect understanding of the very process by which scientists gather knowledge of the natural world. Moreover, correct understanding of vision also led to the precise understanding of visual perspective, which led to the mathematization of space. And without the mathematization of space, there would be no Cartesian coordinates and no Newtonian physics. Now, in Ptolemaic astronomy, physical models were used to show the need to correct Ptolemy's mathematical models. The same Ibn al-Haytham, who pioneered in optics, also laid the groundwork for all subsequent creative developments in Islamic astronomy. Back then, it was more common for a scientist to be able to contribute to more than one field, and Ibn al-Haytham was a universal genius. Now, Ptolemy lived in the 2nd century AD, and he created a mathematical astronomy that was used to predict the positions of planets in the future. As a result, or as a Ptolemy's development connected observational data, a mathematical theory, and then predicted results, which could then be checked and verified. After Ptolemy's mathematical astronomy had been translated into Arabic and studied for about 2 centuries, its flaws became apparent. Some of the most important flaws from the point of view of Ibn al-Haytham were that Ptolemy employed geometrical devices in his planetary models that were physically impossible, i.e. they violated the principles of physics. For example, Ptolemy proposed an equant point, in which parts of the planet's orbit rotated with uniform speed, but whose center of rotation did not coincide with the equant point. Now that works to give good calculations, but is a physically impossible situation. So in this diagram, E represents the equant point, O represents Earth, and T represents the center of rotation of the epicycle on which the planet rotates. So what we've got going on here is that the circle, the big circle, rotates around center T, but it rotates uniformly around E, which is not its center. Now that's a physically impossible situation. Just imagine the Harlem Globetrotters doing their signature basketball spin. If they rotated the balls around a pole different from the actual pole of the ball. Not possible. Now, another way to think about this problem is to imagine making wooden models of the planet's orbits, which Ptolemy himself actually wrote about. It turns out that while Ptolemy was able to model the essential parts out of wood, he could not get them to move in the way his theory required. In order to have a viable wooden model, all of the individual parts must rotate uniformly about their own centers, like a mechanical clock, not speeding up nor slowing down. These devices were necessary for Ptolemy to account for his observations. However, for Ibn al-Haytham, it was just as important to have a set of planetary models that actually represented the heavenly realities in a physically consistent way. This is much like the modern quest for the grand unified theory of physics. There's a sense that scientists have that in the ideal case, all departments of the sciences should be consistent with one another and fit together in one grand cosmological vision. So that's what Ibn al-Haytham felt should be the case. So astronomical theories must be physically consistent, and that didn't exist at this point in time. So Ibn al-Haytham gathered all of these devices from Ptolemy, all of these physically impossible devices, and there were several of them, and he described them in detail in a pivotally influential treatise called Doubts About Ptolemy, which he published at the beginning of the 11th century. This treatise was a catalog of errors and points of improvement to be made in this grand and still respectable theory from Greek antiquity. It led to centuries of new planetary models being proposed and developed along with other astronomical research, and eventually led to a comprehensive planetary model that was completely physically consistent and produced as good results or better than Ptolemy's model. That credit goes to Ibn Ashatir, who died in 1375. Now, Ibn Ashatir was also the official timekeeper of the Umayyad Mosque in Damascus. he was the one responsible for determining the official times of prayers for Muslims. Now, in his model, it looks a lot like Ptolemy's model, but there's additional parts to it. All of the parts rotate around their own centers with uniform angular speeds, which is the original requirement for physical consistency. In principle, this complicated mathematical model could be made into a mechanical model, like a giant clock, not unlike the famous clock made by the Italian clockmaker Giovanni da Dondi in the 14th century. This particular geared mechanism represents the motion of one planet. And here, the whole clock, each panel models a specific planet. So, physical models have been used in the history of science to test the viability of theoretical constructs. If it cannot be made, if a model can't be made, then the theory probably isn't real. Now, in the 13th century, in the early 14th century, a Persian Muslim scientist called Kamal ad-Din al-Farisi, who died in 1319, he worked during the later period of Islamic science, a period that has been mistakenly characterized as devoid of fruitful and creative scientific activity. Al-Farisi was actually a student of one of the greatest Muslim astronomers, Qutb-ud-Din al-Shirazi, who died in 1311. Now, al-Shirazi was part of the tradition of astronomers that I was just talking about, who followed Ibn al-Haytham's suggestions about how Ptolemaic astronomy should be improved. Now, al-Farisi's specific problems or questions were to understand the refraction of light. And he studied Ibn al-Haytham's treatise on optics very closely. That's the treatise where Ibn al-Haytham develops his theory of vision, the intramission theory of vision. And al-Farisi actually produced his own revision of Ibn al-Haytham based on his own experiments. Now, that's how science, of course, advances. Every generation tries to correct the generation before, and that's what happened here. Now, the explanation of the rainbow was al-Farisi's best known achievement, which also required a revision of Ibn al-Haytham's theory of colors. Ibn al-Haytham had proposed that the rainbow was produced by sunlight reflected from a cloud. Al-Farisi's model has the sunlight being refracted twice within the body of water droplets. To discover this, since the actual situation could not be investigated directly, he ingeniously constructed an enlarged model of a raindrop consisting of a glass jar filled with water. He then placed this raindrop model in a camera obscura of the kind that Ibn al-Haytham used so that he could control the amount of light that he projected into the jar. He was able to demonstrate that the rainbow spectrum of colors is produced by the decomposition of light through refraction. So refraction occurs because the different colored light has different wavelengths and therefore bends at a different angle when passing through a different medium. And in the case of the rainbow, the water droplet, as al-Farisi demonstrated, actually produces two refractions of a light ray. In each case, or when it enters the water and then when it leaves the water, including a reflection at the midpoint. And by the time the light leaves the water, the colors are refracted to the point where a rainbow spectrum is produced. Now, he also demonstrated that a secondary rainbow was produced through the same process, through an additional circuit of reflection and refraction. Perhaps you've seen the double rainbow effect in actual experience. Notice that the colors of the second rainbow are in reverse order. Al-Farisi demonstrated that as well. Now, this experiment is similar to the researches later conducted by René Descartes and Isaac Newton, although Newton famously used a prism rather than a jar of water. Also, in one of those coincidences of parallel discovery that were not uncommon from the history of science, an older contemporary of Al-Farisi's in Europe, Theodoric of Freiburg, a Dominican friar who worked in Paris, he conducted a similar experiment and reached similar conclusions. There was, however, no contact between these men, and the only thing they had in common was that they both studied Ibn al-Haytham's optics very carefully. Now, for my last instrument, I want to talk about the Islamic astrolabe. I want to show how another Persian scientist named Al-Biruni used the device to calculate, to determine the circumference of the Earth to begin with. And then I want to talk briefly, give a brief overview of what the astrolabe actually is in terms of it, of being an instrument. The astrolabe actually is a model of the heavens, and it's used for telling time, calculating prayer times, and determining the heights of objects, which is what I want to talk about now. So Abu Rayhan Muhammad ibn Ahmed al-Biruni died in 1048. He was one of the greatest mathematicians, astronomers, and geographers of the Islamic world. He spent most of his career as a captive member of Mahmud of Ghazna's court, which involved several expeditions to India. And during those expeditions, al-Biruni studied Hindu customs, Hindu science, mathematics, and wrote a masterful treatise on the description of his experiences there and a description of Hindu culture. Now, using the sighting tube on the back of an astrolabe, I don't know if you can see, this is my working model, my teaching model of an astrolabe. That's the front with all the parts that I'll talk about in just a minute. On the back, there is this piece called an alidade, and on a real astrolabe, it has a sighting tube that one can line one's sight up from one end of the alidade to another and use it to determine the elevation of a star above the horizon, or to determine the height of a tower, say a minaret of a mosque, or the height of a mountain. And so Al-Biruni used a device like this to determine the height of a distant tall mountain from two observations. These observations were spaced apart by a distance d. So taking these two observations, these two angular results, and putting them together in the trigonometric formula to the right, the height of the mountain could be determined. Now, once the height of the mountain was determined, then using some more trigonometry and one additional measurement, the angle alpha, which is the angle from the angle of the height of the mountain from the horizon, he could then use this formula in the yellow to calculate the circumference of the Earth. And the result he got was very, very close to the modern figure. Quite ingenious use of instruments. Now, the astrolabe, I said, was an analog computer and a portable model of the cosmos, which can represent the positions of the sun and major stars at any time of the day or year for a given latitude. The astrolabe on the right is a famous astrolabe which belonged to a ruler of Central Asia, the famous Ulugh Beg, who lived in the 15th century, who built the famous observatory at Samarkand. He himself, although he was the grandson of Tamerlane, one of the bloodiest conquerors of all time, he was a peace lover and mathematician and astronomer. Astrolabes also were important for the transmission of scientific and mathematical knowledge from Islam to the West. This little device carries a ton of mathematical knowledge in it. A lot of complicated calculations are reduced to simply moving dials and parts and lining things up with and determining results. The Islamic world is also noteworthy for developing other kinds of instruments, like this complicated computer, which determines the Qibla direction to Mecca, the direction that Muslims must face when praying, which is a complicated problem in spherical trigonometry, but here it's been reduced to an analog computer. So the astrolabe, as a model of the heavens now, has several parts I want to talk about in brief. I don't know how well you can see this. Oh, maybe I should get out of the...
Yeah, if you would like, you can actually just stop the screen share to show us the astrolabe and then bring it back when you want to show the components.
Okay, so how do I do that?
So at the bottom where you started the screen share, at the bottom of the screen, yep, there you are.
Oh, okay. All right. And then how do I get back to me? Or can you see me now?
Yep, we can all see you perfectly fine.
Okay, but I can't see what I'm actually showing you. Is there any way that I can enlarge my image?
Yep, we have it enlarged, so we only are seeing your face on the screen.
Are you seeing the astrolabe?
Yep.
Okay. But I can't actually see very well of what I'm showing you. That's the problem.
So if you look at in the top right-hand corner where you have gallery view or speaker view, you would press on
okay, that's
view.
better. That's better. Thank you. Okay, thanks. Okay, so what we have is a coordinate system on the front of the astrolabe. You can probably see those curves that look in a crosshatch pattern. Those represent the sky above the horizon. That's a way of locating the sun and the stars as they appear in the sky. The line here along the bottom is the horizon, and up here we have the zenith. Here we have the meridian line, and so one can trace the path of stars or the sun from when they rise in the morning across the sky, across the meridian at noon, and all the way down to when they set. And then if we take a measurement of a star or the sun, we can line up this moving part to place the sun or the star in the appropriate position in the sky, and then we can read the time from the side. For example, I need to know where the sun is in the zodiac. This is the zodiac coordinate system representing the sun's longitude throughout the year. I need to find where the sun is for a particular day. Let's say it's at Scorpio 10, for example. Then to determine the time of sunrise, I take Scorpio 10 and I line it up with the horizon, which is where the sun actually rises, of course. So I have these two curves, the horizon, Scorpio 10, representing the sun, and I line my rule up with that, and then I can read the time off the side of the astrolabe. I can do it. I can use this device any time of the day or night. During the day, I would need to determine the altitude of the sun, which I can do not by looking at the sun, of course, don't go blind, but there's a way of using shadows, shadow lengths. You determine the ratio of your shadow length to the length of the stick that you're using, and there's scales on the back of here which enable you then to determine the angle of the sun. So you line up the ratio of the scale, the ratio of the shadow to the stick down here, and you can read the angle of the sun off of here. Once I know that, then going back to the front, I take Scorpio 10, which represents the sun, and I line it up to the coordinate line representing the altitude of the sun, whatever I determine. And then I take my rule and pass it through the sun, and I can read the time off the side. To do this at night, of course, what I would do is I would pick a bright star, and the rest of this front piece has stars on it. I pick a bright star. I would use my sighting tube to determine its altitude. Then I'd go to the front. I'd line that star up to whatever altitude I determine. Then at night, of course, the sun is below the horizon. So, and you can't see it, obviously. So I take my rule and I line it up with wherever the sun is, and I can read the time from the side down here. Now, the astrolabe has several other fascinating properties. One of them that I like to use to show students how to use it is to determine the Muslim times of prayer. The 5 times of daily prayer can be determined quite readily with the astrolabe. Let's see if I wanted to cover anything else. I'm going to go back to shared view for a moment. There we are. You can actually make your own astrolabe quite easily. There are computer programs available online that will generate the plates for you. Here's the one I use. Will generate the plates for you, which are the front plate is useful only for a specific latitude. If you change your latitude, you have to have a different plate because it can vary. See, this is on the left we have the plate for London, which is about 51 degrees north latitude. And on the right, we have the plate for where I live in Claremont, California, which is about 34 degrees north latitude. And you can see the difference in the curves. Just quickly, the piece that I was moving on the front has the stars and the representation of the sun on it. You can think of the astrolabe as a clock in the sense that the sun would be at the tip of that red arrow as it then moves throughout the day. The ingenuity of the astrolabe is derived from the fact that it's actually a squashed sphere. It's like the celestial sphere has been squashed down into a plane, which makes it much more durable and actually much more useful and easier to construct than a sphere. So what I was doing on the front of the astrolabe with those coordinates is actually what an astronomer does in a 3-dimensional coordinate system. It's just that the coordinate system has been squashed into a plane. Anyway, let's see. Yeah, so here's the 5 prayer times. They are mostly, well, they're all determined by the position of the sun, whether it's dawn, sunrise, noon, or specific shadow lengths that must then be calculated using the astrolabe, but can be done quite readily. Now, a timekeeper like Ibn al-Shatir would have done these calculations more precisely using trigonometry, but if you're stuck in a pinch and you don't have either mathematical skills or you don't have the time to go through all of that, you could simply use your astrolabe to figure out, well, the times that you're supposed to pray today, for example. And some astrolabes actually have markings on the back. On the upper right of this astrolabe, it shows the time of the afternoon prayer, which is a little bit more complicated. Instead of doing the complicated calculation, one can simply line the device up along those curved lines. Okay, let's see. So, what I hope I've been able to demonstrate is the great ingenuity of Muslim scientists in the use of instruments to investigate nature and to advance our knowledge of the natural world. Thank you.
Hi, Dr. Glenn, we actually have some questions for you.
Okay.
From Facebook. So one question says, were astrolabes used by the general public or just astronomers? They seem complicated.
They could be used by anyone. They are complicated, but they're much more intuitive than actually doing calculations with trigonometry. Astrolabes were used in education, so they would have been used by teenagers and college students in the Islamic world and in Europe to learn basic principles of astronomy. The chief obstacle was that they were expensive, and the really nice ones were made of metal and, of course, very expensive. Now we have reports of some astrolabes being made of wood and paper, but those have not survived.
Hey.
Yeah.
Very cool. This is a more personal question for you. How did you originally become interested in this field?
I started off in mathematical physics, and I was specializing in Einstein's general relativity. So I was interested in astrophysics and astronomy. And then I went to England for a year and studied philosophy at Oxford. And I kind of got more interested in the history of science rather than the practice of science. And so it took a few years to realign myself, but I'm also pretty good at languages, and I decided to study Greek and Arabic, and that's how it happened.
Very cool. And another one for you, again, more about yourself. So what do you wish the world knew more about this area? Let me reread that for you. What do you wish the Western world knew more about in this area?
I wish that my fellow Westerners could appreciate the foundation of modern science, or one of the foundations of modern science, being located within the Islamic world. We tend in the West to think only of our Greek and Roman cultural and scientific forebears, and we forget about the Muslim advances in the sciences. I would like that to be more recognized by my fellow Westerners.
And this question appeared a few times. The astrolabe looks familiar. Is it in the opening scenes of Game of Thrones?
I don't watch Game of Thrones. It probably is. Sometimes the astrolabe is used in programs like that to evoke some of the technical and scientific sophistication of the medieval world. So I wouldn't be surprised.
Thank you so much, Dr. Glenn, for talking with us today and answering our questions. You had some amazing content to share with us, and you have a good evening.
Thank you.
Okay, and everyone else, if you'd like to see more and learn more about 1001, please do come to the Michigan Science Center. Our exhibit is free with general admission, so stop by and join us. Thank you so much, and everyone have a great night. Bye.
Bye-bye.